Welcome to VW 6.4. Today we'll be talking about exponential functions. So the first example says identifying linear or exponential functions. Determine whether the given function is linear, exponential, or neither. And if it's linear, give a function that models the data. Exponential, give a function. So first, let's look at this example here. I can see that we're going down 3 every time. And this is going up by 1. So since this is increasing at a steady rate or a constant rate, this is decreasing at a constant rate, this thing is definitely linear. And we can just think about the equation y equals, I'm going to highlight this row right here. That's the most important one. That's my y-intercept. So I know it's going to be plus 2. And then this right here is our slope. So I'm going to write negative 3x plus 2. And that definitely checks out. If I plug in 1, I get negative 1. If I plug in 2, I get negative 4. If I plug in 3, I get negative 7. So this is definitely good to go. Now if I go to part B, all of these you can actually see they do increase at a steady rate. So I won't write that anymore because I can see that it's just going up by 1 every time. But look here. This is times 1/2, times 1/2, times 1/2, times 1/2. So that's interesting because it's actually halving every time. But now let's say you didn't notice that. Let's say you said, well, minus 16, minus 8, minus 4, minus 2. Though we can definitely see a pattern, you would not say this is linear, right? Because this is not a constant rate here, which is why we want to get rid of this. And you want to write multiply by 1/2 every time. So something like this, when you're multiplying at a constant rate, this is what we call exponential growth, meaning the rate is being multiplied. Because normally we have adding or subtracting. This is now multiplying. And you might recall from our last unit, this is like an arithmetic sequence. This would be considered geometric. So really we're going to be talking about geometric sequences for as far as exponential growth goes. Now for the equation, it's kind of tricky. The general form we're going to use is this, a b to the x plus k. This b, think of it as like your growth rate. This k is obviously going to be your vertical shift, if there is one. And then this a is often thought of as like your starting value. So it is pretty similar to geometric sequences, just a few changes. Now for starting value, what I mean is this right here, your y-intercept. I can see that the y-intercept is 16, so I want to put 16 right there. The rate is 1/2, so I want to put 1/2. And I just put an x right here, and there it is. There's our exponential function model. And I can definitely verify that, because if I plug in 0, I do get 16. If I plug in 1, I do get 8. If I plug in 2, I definitely get 4. So that checks out. And then for the final part, let's look right here. This is going up 2, up 3, up 4, up 5. So definitely not linear. And there's no constant multiplier. This would be times 2, and this is times some fraction. So this is going to be neither. There's really no function, exponential or linear, that I can model with this. Okay, so that's our part 1, looking at tables here. Now let's talk about the actual graph itself. So now we're going to graph this thing, 2 to the x. So just to make sure we understand, I want to make a chart here. Let's start with -2, -1, 0, 1, 2. If I plug in 0, I get 1. If I plug in 1, I get 2. 2, I get 4. -1 would be 1/2. -2 would be 1/4. And let's plot those points down. 0, 1, 1, 2, 2, 4. And right here, there's our graph. Now what's really cool is notice how no matter what number I plug in for like x, like what if I plugged in like -10? That would be 1 over 1024. It'd just be a really, really tiny number, which means this thing is just going to get closer and closer to 0 and never actually hit or cross it, which means I have a horizontal asymptote right there, right at 0. So we can write that in. You have your HA, y equals 0. And I can see my domain and range. My domain is everything, while the range would be 0 to infinity. And notice how the 0 is non-inclusive. So now let's try a couple of harder graphs here. So think of this thing as like your parent graph. We'll call that letter A. A little bit harder now. It says 1/2 to the x minus 1 minus 2. I'm going to do a little bit of algebra here. 1/2, that's 2 to the -1. And I can leave the x minus 1 there, minus 2. I write it like that because now I can see the parent graph is the thing we started with, 2 to the x. That -1 is going to reflect over the y-axis. And then there's a shift. I'm going to go right 1 and down 2. Now, a lot of people want to do this, like y times 2, because you see a 2 right here. Make sure you don't do that. If you have a stretch, you'd actually see a number out here. Like you would actually see a 2 times something there. This 2 right here is the parent graph. That gets accounted for right here. So you don't want to put this there like unnecessarily. So now let's actually graph it. So reflect over the y-axis and then right 1 down 2. So let's grab this point. If I reflect it, nothing happens. Go right 1 down 2. So 1, -1 is my new point. Let's reflect this over the y-axis and then right 1 down 2. And then if I really think about this horizontal asymptote here, it's at 0, and then this -2 then shifted down 2. So I'm just going to put my asymptote right at 2, because that's going to help me actually see the graph. Because from there we kind of get the gist of it. These 2 points are enough to just kind of see that the graph should look something like this. And I'll leave it like that. And I'll do my domain range. I can see the domain is still everything. The range is now -2 to infinity. And what's really helpful is to notice that this thing right here, that actually tells you your HA value. So that's very helpful. Let's try one more graph. Let's call this one C. I'll do it in blue. Again, I can see my parent graph. That's 2 to the x. And then a couple of things are happening. Reflect over the x-axis, or sorry, over the y-axis again. If the negative were on the outside, that would be the x-axis. And then x times 1/2 is what a lot of you would write, right? Because it looks like a half. But remember that it's actually the reciprocal. This is x times 2. And then I see it up 1. So let's do that. What some people do is they actually put the asymptote first so they can kind of make sure they're doing it right, because I know the asymptote should be at 1. So I'm just going to plop that in right there. And then I'll reflect and do x times 2. So if I grab my parent point, reflect it, nothing happens. And I'm going to do x times 2, nothing happens. So I'll go up 1. So here's my new point right there. And then the next point, let's grab this one. This is 1, 2. If I reflect it, it goes here. If I do x times 2, that becomes negative 2, 2. And then up 1, right there, negative 2, 3. And right there is our final graph. There's part C. Let's do domain range. Domain is still everything, and the range would be 1 to infinity. And just to label, I'll better put my asymptotes in here. Y equals 1, y equals negative 2. And that's it.